What's the minimum value of 2 over sine x plus sine theta plus 3 over cosine theta, where theta is restricting between 0 and half pi? And so we're going to use this lemma, this inequality, special case of Holder inequality. First let's write down Holder inequality. It says if 1 over p plus 1 over q is equal to 1, where p is strictly than 1, which, by the way, implies q must be also strictly bigger than 1, and where all the a's and b's are strictly positive, then we always have, in fact, let's use xi and yi, because here I already use a's and b's. So xi, yi, we always have x1 times y1 plus all the way to xn times yn is always less than or equal to x1 to the p plus all the way xn to the p to the power of 1 over p times y1 to the power of q plus all the way up to yn to the power of q to the power of 1 over q. This inequality is always true. So knowing this fact, this for a fact, right, we're going to prove this lemma. Let's say this time I let p equals n plus 1. Right? Because here it says this inequality is always true whenever p is greater than 0 or less than negative 1. Right? So here n plus 1 must be greater than 1. Right? So now I can use this condition. Right? This condition is satisfied. And this is fine. And so in that case, I can rewrite, before I rewrite it, I want to express q. Right? P is equal to this. What's q? Right? Q. 1 over q. 1 minus 1 over p. 1 minus 1 over n plus 1. N plus 1. M. So therefore q must equal n plus 1 over m. Now I can rewrite this inequality. Therefore I have x1, y1 all the way xn, yn no larger than x1 to the n plus 1 all the way xn to the n plus 1 to the power of 1 over p, that is 1 over n plus 1 times y1 to the q, like I said, n plus 1 over m all the way yn to the n plus 1 over m to the 1 over q. 1 over q is this bit, m over n plus 1. Okay, so right now I let xk times yk, right, using substitution, equals ak in general. Right, k goes from 1 to n, because in the end I want to represent x and y's in terms of a's and b's. Right, so in this case, I easily have xk is equal to ak over yk. Right? So easily xk to the n plus 1 is equal to ak to the n plus 1 over yk to the n plus 1. I still have y's in here, but in the end, I want to replace all the y's with b's. And maybe I can let here, I'll let yk in general, yk to the m plus 1 over m, I'll let it equal to bk. I don't know exact, so, but I can use substitution, right? It's just some fixed value, right? Some substitution, right? That's fine. So now I can somehow represent yk, right? Raised to the power of m on both sides. Right? So m plus 1 equal bk to the power of m. Right, now what do I have? Right? Now that means I can just replace yk to the m plus 1 with this bit. Right? So now, all of a sudden, I can rewrite this into ak to the m plus 1 over bk to the m. Right, now, there's no more x's and y's, there's only a's and b's. Right? Now all of a sudden I can rewrite this inequality into, now left hand side must become a1 plus all the way to an less than or equal to right hand side is what? Becomes, like I said, in general, xk to the m plus 1 becomes this. Right? So becomes a1 to the m plus 1 over b1 to the m, or all the way an to the m plus 1 over bn to the m plus 1, or to the m, excuse me. So this time, bracket to the 1 over m plus 1 times this bit. Like I said, each of them have now become bk, right? B's, b1 plus all the way to bn to the m over m plus 1. Here we just raise to the power of, let me see if the inequality changes. M greater than 0. Let's just consider the first case where m is greater than 0, so it's greater than 1. No problem, right? Raised to the power of m plus 1 on both sides. Right? Inequality remains. So left hand side, a1 all the way to the m plus 1 less than or equal to, so this power is gone. Right? So a1 to m plus 1 over b1 to m plus all the way an to m plus 1 over bn to m. Right, this power now becomes just m. Right? b1 all the way bn to the power of m. Now I just divide this over. Right? So every b is, is positive. Right? Because every x is and y is positive. Right? So a's and b's are all positive. This doesn't change the direction. So easily I can just divide it. b1 plus or bn to the power of n. And so this is indeed true. When m is greater than 0. Right? But if m somehow is less than -1, right? So in that case, then that means n plus 1 has to be negative. Right? Then we cannot, cannot satisfy this condition. Right? We can n plus 1 negative. No, cannot. We have to use some other, right, when m is less than negative 1. So that means negative m is greater than 1. Then we let p equal negative m. Right? So in this case, this condition is satisfied. And then we use similar technique. I'm not going to dig in details into that, but similar, same, exactly, almost the same technique, and you can finally reach the same conclusion, just changing direction of inequality in somewhere. And also, this equal sign holds when every pair of A1 over B1, they are all in proportion. AN over BN equals some constant. So right now, how can I apply this inequality to find out the minimum value of this? How can I perhaps rewrite this original expression into some nicer, nice other form? And that form can be greater than or equal to, I suppose, because we're finding the minimum, right? Greater than or equal some, I suppose, sine square plus cosine square. Right, because that's one of the identities we know about trigonometry. Right? If we can somehow reach into this destination, right, by the way, to the power of m, right, when we determine m, right, in this case we have two pairs of numbers, so n equals 2. So let's determine m. What could n be? Right? If we construct some guess and check, trial and error. Right? Suppose this is the final, result. So here we go. So B1, right? In that case, looks like B1 must be sine square. B2 must be cosine square. Let's just say B1 sine square. B2 cosine square. All right. So what's B1 to the power of m? B1 to the power of m, somehow I want B1 to the power of m equals sine. Right, this is what I want. I want it equal to sine. So looks like sine squared to the power of m equals sine. So m must be half. Right, let's see if that works in our favor. All right, so that means m is half, so to the power of half. All right, what's A1? What's A2? All right, so which means m plus 1 has to equal 3 over 2. Right? All right, what's A1, A2? So it looks like here I have A1 to the 3 over 2. Right? So that means I must rewrite 2 into some other, to some number to the power of 3 over 2. So I can just rewrite into 2 to the power of 2 over 3, then to the power of 3 over 2. Right? That's the same thing. All right, so which means I do the same thing to 3 to the power of 2 over 3, then to the power of 3 over 2. So now it's clear. A1 is, can treat 2 to the power of 2 over 3 as A1. A2 I can use 3 to the power of 2 over 3. Right? like I said, b1, b2. So okay. So b1 to m, b1 to the half. So sine square the half. Likewise, cosine square to the half. Right? So m power m plus 1, m plus 1. Everything is in this form. Right? This looks nice. So greater than or equal to, I just add up the a's. Right? 3, 2 over 3. Add up the a's, then raise to the power of m plus 1. That is 3 over 2. That's constant, of course. Some constant, right? I'm not going to calculate its exact value. Right? It's only when the equal sign holds only when a1 over b1 is equal to a2 over b2. Right? That is 2 to the 2 over 3 over sine square is equal to 3 to the 2 over 3 over cosine square. Right, that is easy. Theta is in between 0 and half pi, so sine is positive, so is cosine. So we take the square root on both sides. Right, so now it just becomes cubic root of 2 over sine is equal to cubic root of 3 over cosine. Right? Tangent theta is just multiply sine over here, divide this over there. So tangent theta, that is immediately cubic root of just 2 over 3. So it's only when theta is equal to arctangent of cubic root of 2 over 3.